In this video, let us solve the October-November 2024 0620, that is the IGCSE Chemistry paper 6-1, that is paper 6 alternative to practical with all the examination tips. So let's go ahead and solve this paper. But before we go ahead, let me explain you and show you something. This is an IGCSE app which is very easily available on chemscience.in website, where you can get access to many resources like topics, past papers with MS, revision test, and let's see what is there inside the topics. Now inside the topics you will be able to see all these chapters. In the chapters again you will be able to see the study material, that is notes, videos, subjective test and MCQ test. Actually these are the worksheets and not the test. But yes, with the MCQ you can definitely find out your score, that what did you understand and how much can you score in the MCQ test. In the subjective worksheets also you will be able to see the MS at the end. Yes, let's see what is there in the notes. Yes, you have in one chapter itself you have notes of all the subtopics also, like as shown here. Now as mentioned here, the revision test is given. In the revision test you can choose your own chapters or topics and select whether you want the revision for MCQ questions or the subjective questions, and this revision test will create a revision test for your selected topics with the MCQ or the subjective or both for the practice. So just go ahead and download this app on your phones. Yes, now let's start with the question 1 of this question paper 6-1. Here is question 1, where a student has a mixture of copper 2 carbonate powder and crystals of sodium sulfate. Now remember, you have copper carbonate and sodium sulfate. Copper 2 carbonate is insoluble in water and sodium sulfate is soluble in water. Now we have taken the mixture of two substances, out of which one is insoluble and one is soluble. The student tries to obtain pure copper 2 carbonate and crystals of pure sodium sulfate from the mixture. Show your figure 1.1 shows 4 of the steps that students carries out, and here are the steps, where the step 1 is adding a distilled water and stirring. Filter the mixture in the step 2. Step 3 is heat the filtrate from the step 2, and step 4 is leave the residue in the filter paper from step 2 in a warm dry place. So here are the sub question 1. It says state what happens to the sodium sulfate in step 1. Now what is step 1? Step 1 is adding distilled water and stir. Now as we already know that the sodium sulfate is soluble in water, so what will happen in step 1 is that sodium sulfate will dissolve in distilled water. That is what is going to happen, or you can say it will disappear, or but then I feel dissolve is a better word because it's clearly written it's soluble. Now the B part is state what is removed from the filtrate in step 3. Now what is step 3? Step 3 is here heating up the filtrate from step 2 until the crystals start to form. So what are we removing if in step 3 from the filtrate? So we are removing water, that is we are evaporating out the water to by heating it, and that's why the removal of water is done. Now the C part is describe what must be done after the filtrate has been heated in step 3 to obtain a larger amount of sodium sulfate crystals. Now once we have heated, what is step 3? Let's see the step again. It's written heat until crystals start to form. So the crystals have started to appear, it's seen. So after that we can cool it down to get the more crystals. Cool it down, cool the whatever solution we have taken in the evaporating basin, cool it down. Or you can say allow it, stand it for some time to cool down. You can even write that. The next part is D1, state what must be done to the residue before it is allowed to dry in step 4. Now in step 4 We had just left the filter paper to dry to get the residue, that is the copper carbonate, which is insoluble. Now in step 4, what was the question is, what must be done to the residue to before it is allowed to dry in step 4 to obtain pure copper carbonate. Now if we want to obtain pure copper carbonate, we need to wash it, or you can say rinse it with distilled water twice or thrice. Distilled water to remove all the impurities, or you can say the sodium sulfate molecules which are stuck with the copper carbonate, to get the pure copper carbonate. Let's see, the second part is identify the substance removed from the copper to carbonate in D1. Now as I've already said, the sodium sulfate molecules might have stuck to the copper carbonate molecules, and that can be washed off with the distilled water. So we are washing it with the distilled water to get pure copper carbonate. Now that's it, question 1. Let's see what is question 2. Question 2 is here. A student investigates the reaction between aqueous magnesium sulfate and aqueous barium nitrate. Remember, it is magnesium sulfate and barium nitrate. Now a precipitate of barium sulfate forms in this reaction. The student does 8 experiments. Now here is the whole procedure, where fill a burette with the aqueous magnesium sulfate, run some of the magnesium sulfate to level up the magnesium sulfate on the burette scale. Same again, fill the burette with the aqueous barium sulfate, repeat the same procedure to level up on the burette scale. Now add 4 centimeter cube of magnesium sulfate from the burette into a measuring cylinder. Remember, 10 centimeter cube measuring cylinder. Add 1 centimeter cube again of the barium nitrate from the second burette in the measuring cylinder. So what are we doing? We are taking a measuring cylinder, we are adding 4 centimeter cube of magnesium sulfate first, and then 1 centimeter cube of barium nitrate. Place a stopper on the top of measuring cylinder and invert the measuring cylinder several times. Now we are stopping, add a stopper and mix it thoroughly. Leaving the measuring cylinder to stand, we are allowing it to stand for 15 minutes. Record the level of the precipitates of the measuring cylinder scale. Rinse the measuring cylinder with distilled water. This is the procedure. Now in the experiment 2, we are repeating, but using 1.5 centimeter cube of barium sulfate instead of 1 centimeter cube. Now remember, in this step here we had added 1 centimeter cube of barium nitrate to the measuring cylinder. 4 centimeter cube of magnesium sulfate was taken. That has to be maintained. That is, in the second experiment, again we are taking 4 centimeter cube of magnesium sulfate, but we are adding 1.5 instead of 1 barium nitrate. Now the next experiment is using 2.5 centimeter cube of barium nitrate, and so on. 2.5, 3 centimeter cube, 3.5, 4.5, 5 centimeter cube, and then 5.5. This is how the 8 experiments are done, and different level of precipitates are obtained. So here is the table we need to complete. As we know, the magnesium sulfate is kept steady 4 centimeter cube, so we are adding 4.0 everywhere till the 8th experiment. So here is 4 centimeter cube. Now next time we had added 1.5 centimeter cube of barium nitrate. In the third experiment it was 2.5, 3.0, 3.5, 4.0, sorry, not 4.0, it was 4.5, 5.0 and 5.5. This is how you are going to add as per the experiment. Here this is the level of the barium nitrate we are adding. Now let's see what is at the downstairs. Yes, in this the measuring cylinder pictures are shown where the level of precipitates are shown, and we are supposed to note down the level of precipitates on the measuring cylinder. The example is given 1.2 because this is 1.2 level of precipitates. So here if we check, it is 1.8 centimeter cube on the measuring cylinder. The third one is exactly 3, so we can write 3.0. The next one is 3.6, so 3.6. Next is 4.2, then here is 4.6. Next is 4.6 again, yes, 4.6, and again 4.6. So now the level is maintained, and here is how you're going to write to 1 decimal place of all the levels which we have, which we can read in the measuring cylinder scale. So here we fill up and complete the table. Now here is a question B, which says complete a suitable scale on a y-axis and plot the results from the experiments 1 to 8 on figure 2.1 here shown. Draw 2 straight lines. Remember, we are supposed to draw 2 straight lines and of a best fit through your points. The first straight line should be for the first 5 experiments. Remember, for first 5 experiments, we are going to draw the first straight line and must be extended to pass through 0.00, that is origin. The second straight line should be for the last 3 experiments and must be horizontal. Extend the straight lines so that they cross each other. Now here is the scale graph grid where we can see that on y-axis we have level of precipitates on the measuring cylinder scale in centimeter cube, and on x-axis we have volume of aqueous barium nitrate in the precipitates. Remember, we need to draw the crosses so that the points are very clearly visible. So now here we have plotted all the points. Now let's join all these points with 2 straight lines. So now here are the 2 intersecting lines, 2 straight lines, one passing from 0 and the other 3 lines, 3 last points which are again joined by a straight line intersecting at this point. Now the question C is use figure 2.1, that is the graph grid, deduce the level of the precipitates on the measuring cylinder scale when the experiment was repeated using 2.8 centimeter cube of aqueous barium nitrate. Show clearly on figure 2.1 how you worked out your answer. Remember, it's 2.8 centimeter cube. Now here you can see that I have drawn 2 dotted lines from 2.8 centimeter cube of aqueous barium nitrate, extended it on the straight lines, and here we obtain it as 3.3 centimeter of the precipitates, level of precipitates. Now I have drawn it with red, but you are supposed to draw it with the pencil only. So our answer is 3.3. So let's write it as 3.3 centimeter cube of the level of the precipitates on the measuring cylinder. Now a student repeats the experiment using 6.5 centimeter cube of aqueous barium nitrate. Predict the level of the precipitates on the measuring cylinder scale. Now we know that after certain state we had obtained, here we can see that after the last 3 reading was 4.6 only, after that is 4.5 centimeter cube of aqueous barium nitrate was added. So even if we add 6.5 centimeter cube, the level will remain same. So 4.6 centimeter cube of the precipitates will be seen, and the reason is that the experiment is over, or you can say the reaction is over, reaction is completed, and all of magnesium sulfate, has reacted. So it's over now, magnesium sulfate has fully reacted, and so no more precipitates will be added on to 4.6 centimeter cube. Here is E. Sketch on the figure 2.1 the graph obtained if all the experiment was repeated using aqueous barium nitrate of half the concentration used in experiments 1 to 8. Now here that says sketch the graph again if all the experiments are repeated using half the concentration of barium nitrate. So if half the concentration, here is the grid, and half the concentration is used, half the level of the precipitates will be seen. So here if we have 1.2, we will get a graph at 0.6, which I am drawing here. Now I have drawn the points in the gray or the black. You can see here are all these points. Now I have drawn these points exactly half of the value which I have shown here, which is given in our data. So if we draw a straight line, it's going to continue, because then in this case if the barium nitrate concentration is half, the magnesium sulfate will not fully get reacted, and so the line will continue, it will not level off this way. And if we join these points, this straight line will continue till end without getting leveling off, because yet the level to achieve all the magnesium sulfate get reacted and the highest level of precipitate will not be achieved. So this is the second line which will draw, which is again an inclined vertical line going straight off vertically high. So yes, the E part is completed. Let's go ahead with the F. It says suggest why the measuring cylinder is inverted several times after the aqueous barium nitrate is added. That is to stir it well, or you can even say mix it well, because we want the maximum amount of precipitates. Now the G question is suggest why the measuring cylinder is left to stand before the level of the precipitate is recorded, so that all of the precipitates settle down well so that we can measure the level. Let's see H question. The volumes of both the aqueous solutions are measured using burettes. Now the question is, give a reason why burettes are used rather than the measuring cylinder. Now we know that burettes are more accurate. Now burette is more accurate than measuring cylinder, so we get a better level of precipitates every time and no error is seen. Now the sub question 2 is suggest why the burettes are used rather than the volumetric pipettes. Now if we want to measure the varying volume, we need to use the burettes. Now volumetric pipettes can measure only fixed volume, so we can say that to measure the variable volumes of the solution or solutions. Yes, so this is how we use burettes and not the measuring cylinder or the pipettes, and that's the advantage of burette. You can say that it's more accurate as well as it measures the variable volume. Now here is question 3. So question 3 is a student test two solids, solid T and solid U. Now the test on solid T is given here. Remember, so it is solid, neither liquid or aqueous or gas, so it's solid T. Now solid T is lithium sulfite. Complete the expected observations. Now a sub question is, the student carries out a flame test on solid T. Now let's see what flame test can be given by either lithium or sulfite. It's actually the metal which gives the flame test. So let's check in the qualitative analysis table that what flame color does the lithium give. So here are our tables of qualitative analysis, and yes, flame test. Yes, here are our flame test for the metal ions, and lithium ion, we can say it is a red color flame. So we can write that. But yes, along with that, let's also check about the sulfite ions. What's the test given by the sulfite ions? Yes, here is the sulfite ions, that is SO3 2 minus given. And for the SO3 2 minus, we can say that here we can add an acidified potassium manganate, and the acidified potassium manganate color changes from purple to colorless. That's the test given by the sulfite. So let's remember that also. Yes, so if we write the flame test on solid T, that is lithium sulfide, the observation should be the red flame. Yes, for the lithium ion. Now the student dissolves the remaining solid T in water to form solution T, and the student divides T into two portions. Now the student adds the first portion of solution T on a test tube containing acidified aqueous potassium manganate, and that we have already seen that it is the test of the sulfite ion. So state the color change. It will be purple to colorless. Purple to colorless. That's the color change on adding aqueous potassium manganate, that is acidified aqueous potassium manganate. The sub question C1 is, to the second portion of solution T, the student add excess dilute nitric acid. The gas produced turns filter paper soaked in acidified potassium manganate white. Identify the gas produced. Now for that also, let's check the test for the gases, and let's see. Now here are the test for gases, and we can say that here the acidified aqueous potassium manganate from purple to colorless, it's the SO2 gas which turns it purple to colorless, or you can say white color, which we have already seen. So the gas produced will be SO2 gas. So let's write here, identify the gas, that is sulfur dioxide gas. Yes, the second portion is to the solution produced in C1, the student adds aqueous barium nitrate. Now on adding a nitric acid, the solution of lithium sulfite will change to lithium nitrate. Right, and now in this, if we are adding barium nitrate, the barium nitrate is a test of sulfate ions, SO4 minus, but the resulting solution contains lithium nitrate, so there should be no color change, or you can say no observation. So this is what you can observe with barium nitrate. Let me repeat that barium nitrate is a test of sulfate ions, but our solution is lithium nitrate, so as we don't have sulfate ions, there won't be any color change. Let's go ahead with the next part. In this, it's test on the solid U. Now solid U contains a one cation and one anion. Yes, we are given one cation and one anion. Now table 3.1 shows the test and the student's observation for solid U, and here are the tests given. Here it says, to the first portion of solid U, add a few drops of aqueous ammonia and green precipitates are obtained. To the second portion of U, add 1 centimeter depth of dilute nitric acid and a few drops of silver nitrate and yellow precipitates are obtained. Now if you're going to check the cation and anion table, you might find that the silver nitrate test is the test for chloride, bromide and iodide test, and if we get yellow precipitates, it's the positive test for the iodide ions. But yes, we'll check the table at the end. To the third portion of solution U, add 1 centimeter depth of aqueous chlorine and the solution turns brown. Now remember the test, it's aqueous chlorine that turns solution brown. Now identify the two cations that the test and the observations in table 3.1 show could be in solid U. Now two cations they are asking. The cation test here is one, that is green precipitates, and let's see what other it is possible. So identify two cations that the test and the observation in table 3.1 show could be in solid U. Now let's check the table of the cation test. Now here is the test table of the cations, and we can say that here on adding aqueous ammonia we are having green precipitates for two of the cations, that is chromium and Fe2+. So probably these are the two cations possibly present in the solid. Yes, so let's write our answer that chromium 3+ ions and Fe2+ ions. These are the two cations possible in the solid U. Now question E is describe an additional test that the student could do to confirm which one of the two cations identified in D, that is this one, the two cations in solid U. Give the expected results for one of the cations. So here is the table again, and let's distinguish how can we find out that chromium 3+ or Fe2+, how can we distinguish the two ions? Now we can see here that the green precipitates are insoluble in excess for the ammonia, but if we talk about the aqueous sodium hydroxide, and if we add sodium hydroxide dropwise, we get green precipitates for chromium 3+ ions, but it is soluble in excess sodium hydroxide, but Fe2+ is insoluble in excess of sodium hydroxide. Also the precipitate turns brown near the surface on standing. So this is how we can distinguish the two ions, by adding excess of sodium hydroxide, that is for chromium the green precipitate is soluble in excess. So let's write that here, that add excess of aqueous sodium hydroxide to the solution, and the cation is Cr3+, and the result is the green precipitates are soluble in excess, or we can even write dissolves in excess. Now identify the anion in solid U, and we have already identified that it is iodide ion because the silver nitrate test gave the yellow precipitates. Now yellow precipitates are for iodide ions. Now let's see the last question. The last question 4. Beetroot is a colored vegetable. The color is caused by a mixture of water-soluble colored compounds. Plan an experiment to find how many water-soluble colored compounds there are in a beetroot. Include in your plan how to extract the colored compounds from the beetroot, how to separate the mixture of the colored compounds, and how the results show how many colored compounds there are in the beetroot. You are provided with a beetroot, distilled water, and common laboratory apparatus. Now here in this question we can see it is 6 marks question, and we are given enough space to write the answer. And it's also said that we are going to separate the colored pigments, the colored compounds present in the beetroot, which are water soluble. So now the only process which is used to separate the colored compounds is the chromatography. Everyone knows it is chromatography. So if we are going to use that, we just have to describe the process of the chromatography experiment and how we are going to do that. The first thing is we are supposed to cover how are we going to extract the colored compounds from the beetroot. So what are we going to do is, so first point what we can write is that crush the beetroot with the help of pestle and mortar. Now remember, we are going to mention all the apparatus whatever we are using as far as possible. If possible, we can mention its capacity also, but here we don't need to mention the capacity of pestle and mortar, so we're just mentioning the pestle and mortar. Then we can add distilled water to it and filter the content filter the content to get the colored compounds in water. The next point we can write is that add a drop of this solution on a pencil line on a chromatography paper drawn near the bottom of the chromatography paper. So what we're going to do is that we need to have a chromatography paper near the bottom. We are going to draw a baseline with the pencil and we're going to add a drop of this solution. That's why we have written add a drop of this solution on a pencil line on a chromatography paper drawn near the bottom of the paper. You can even use your own language to describe this. So this is my point of view. Now what we can do is that take little water in a beaker and hang the paper in it, that is in the beaker, in such a way that the pencil line or the origin line, also you can mention, the pencil line is above the level of the solvent, Now what solvent have we taken? Above the level of the water, because we have taken water as a solvent. This is the third point we are going to mention. And then we can say that allow to stand for some time till the level of the solvent rises near the top of the paper, Next is allow it to dry. We can see the different colored spots separated on it. Now let's check what is the question again. Here the question says we are supposed to cover how to extract, that we have done. The second point is how to separate the mixture of the colored compounds. That's the chromatography method which we have used. And the third point says how the result shows how many colored compounds there are in a beetroot. So now we are supposed to conclude that how can we find out that how many colored compounds are there. So let's write about the conclusion, that the number of different colored spots on paper gives us the number of different compounds present in beetroot, right? So it's, if there are suppose two different colored spots seen on different places, that shows there are two compounds. If there are three spots seen of the colored compounds, then we can say there are three colored compounds present in the beetroot. So this is how we are going to conclude. So this is last question carrying 6 marks. If we have written all these points, then definitely we're going to get full 6 marks. Now I'll again repeat that we need to fully describe the process. Describe process, also mention the apparatus which we are going to use, so mention the apparatus. And if suppose if there is some other experiment, if we are describing, then capacity is required, then we can mention the capacity of the apparatus also. Here it was not needed, so we just had to describe the process, and we also mentioned the apparatus required, that is beaker, pestle and mortar, the chromatography paper, all that we had mentioned. So this is how we are going to describe the last question of the investigation, and this is definitely required. All these points have to be taken care. I think the whole paper is very clear. Also go through the link given in the description, which will help you download the app for IGCSE for further practice.